Okay, so I also want to change the notation a little bit because I feel that I've been using the wrong notation. So for example, what I would like is that if I'm using the total angular momentum and I have J3, then its eigenstate should really be denoted by Jm. And if I'm using orbital angular momentum, then its eigenstates should be Lm. And if I'm using spin angular momentum, then its eigenstate should be labeled by Sm. Okay, so I used L before, but it should be in the context, it should be a different letter. I mean, they all have, I mean, J will have the value of, Jj plus 1. This will be the value of, say, J squared. And this will be the value of L squared eigenvalue. And this will be the value of S squared, okay? This is just notation.
Sir, what is the difference between J3 and L3?
There's nothing. It's just like, they take the same, they have the same kind of, they have the same values, but in the context, L is used to denote, orbital angular momentum. S is used to denote spin angular momentum, and J is used to denote, in both. Both are the sum of both.
Yeah, so it's usually the total angular momentum, right?
Yeah, the total angular momentum, yeah. Okay, so this is just a notation. So, this is just a notational point, okay? The analysis we did is valid for all these things, but we will soon see that this thing, actually can only take a subset of those values. That is my next point that I want to show. Okay, it cannot, the orbital angular momentum cannot take half integer values. That's something I will show right now. Okay, so we've just seen that the orbital translation around a circle is given by the orbital angular momentum. So generated. So suppose that we are rotating a system. So suppose that we are rotating a system which is in state. It's given by a state Lm by an angle. Sorry, angle, angle 2 pi, okay? Then around, say, the z-axis. Then our formula is e to the power minus I 2 pi Lz. Can you just wait 1 second? Okay. Okay, sir. Okay, is that clear? Why this is the case? Because we saw that the operator that translates by this angle is minus I alpha n dot L. And here we are taking the n direction to the z direction. So this is Lz. And the angle, we are taking this to be 2 pi. So this operator becomes this operator. Is that clear?
Yes, sir.
Okay, good. So if I apply this on, Lm, what am I going to get here? Okay, let me ask a simpler question. We're going to, of course, have e to the power minus 2 pi, and then what? What is the eigenvalue of Lz?
The eigenvalue of Lz.
Which is what? M, right?
Um, which is
it M? Nahi?
I'm not sure.
So m h bar.
Yeah, h bar is we are defining h. We have absorbed h bar in Lz, in the definition of Lz. So, or you can say we are using this h bar equals to 1 units.
Yeah, then it's just m, right?
Yeah. So Nahi, why aren't you sure? What is L's? What do you get when you apply Lz on Lm?
Oh yeah, I'll get m.
Right. And now if
I
I
was
raise to a power n, you'll get m to the power n.
yes.
So, and if I now add Lz into a power series, I will get the same power series, but Lz, there should be an I, right? That's what's missing. The I should be, yeah, okay. Are you convinced now?
Yes, sir.
Okay. But we know that our rotation operator is also a translation operator. Now, what is our translation operator? And if I do a rotation through twice pi, what is the translation vector going to be?
0.
Very good. Then what is the translation operator going to be?
The rotation operator by 2 pi.
No, let's look at the translation operator. It's e to the power minus I by h bar a dot p. So if this is 0, what happens to this operator?
So identity operator.
Yeah. Now, hey, is that clear?
Yes, sir.
Okay. So this thing is equal to this thing. So what can we write about this? This has to be 1. Because this is nothing but rotation by 2 pi, which is equal to no translation, no net translation, right? So that operator should be the identity operator. This operator should be the identity operator, right? Is that clear?
I'm still kind of like processing what's going on right now.
Okay, let me recapitulate, okay? The rotation operator through an angle alpha around some axis n is given by E minus I alpha n dot L. We have proved that, right?
Mm-hmm.
But this operator is also a translation operator in which you translation by some translation vector A. Now this translation vector, what it is, will depend on this angle. If I do the rotation of my system through an arc, then that translation, vector is going to be this vector, right? This is going to be A. And this will be alpha. Do you agree?
Yeah.
Now, what I'm saying is that what if I put alpha equals to 2 pi? What is going to be A?
It doesn't change. It's the same.
A is, what is A?
0.
0. Okay. Now, from the explicit expression of A equals to 0, what do we know about this thing? What is this going to be? Here.
Translation. Yeah, this one.
So
Right,
can I do this? If I put 0, exponential to the power 0 is what?
It's just the identity 1.
It's the identity operator. Okay? In the case when alpha is 2, in the case where A is 0, right? This is what it is. But in that case, what is the angle of rotation? It can be either 0 or it can be 2 pi, right? So rotation by 2 pi should be equal to the identity operator. Do you agree?
Yeah.
Okay. Now, what is the expression for rotation by 2 pi? Suppose I choose this n direction to be the z direction. Okay. Then we see that it's going to be minus 2 pi I m. Right? But we know this has to be equal to 1. Let's just call it 1. The identity operator is ujjo, as we say in Bengali, is there. But so for this to happen, what constraint do we have on the values of m? Can m be a half integer?
No.
So m needs to be an integer, right? So this implies that m is an integer. Okay? You know that, right?
I'm actually having a bit of a problem convincing myself that for alpha equals to 2 pi, A will be 0. Because like I'm trying to think what will happen.
You have to go and do it yourself, because you have the background to be able to do that. Because what you have to do is that you have to convince yourself, okay, what if I do a small angle, and then these are the small a's, and then this vector algebra gives me this, and if I keep on adding, what happens to A, and if I keep adding, if I keep rotating, what happens to A, this, and I keep, right? So that you see that at the end of the day, you'll get 0 as you come back. Okay?
Yeah, I'll do that. Yeah.
Okay. But what we have shown is something very remarkable, is that for the orbital angular momentum, m can only be integer. If m is an integer, L can only be an integer. Can only be a positive integer. Can L be, if m is an integer, can L be anything else?
No, because L represents the maximal value of M.
Correct. So we conclude that the orbital angular momentum number L can only take positive integer values. This is remarkable. So because we saw that our analysis of the angular momentum algebra allowed the eigenvalue of the angular momentum squared operator to be half integer. But that's not true for the orbital angular momentum, and we established that by connecting the orbital angular momentum to the translation operator, and then showing that translation around a circle is the identity, and therefore L can only be integer. Okay.
Sir, so can S can take both, like half?
Yeah, S can take both.
Yeah. Okay.
Because
only
S
L
doesn't
has
have this connection to a translation around a circle.
Okay.
Okay? This is very non-trivial, very simple, but very non-trivial, okay?